Okay, so where we are now is we're getting into the liquid phase. So if we can draw this TX phase diagram, let's draw a really long one. We have temperature here and composition A10. And so way up here we have gas, and then there's some boiling points here. So those are the boiling points of A and B. And then we'll have some vapor pressure curve. So this would be the YA curve. And the XA curve. And that makes sense that YA would be to the right. So like if we boil something right here, A is the lower boiling point, so it's going to be the more volatile thing, and so it's going to be enriched in the vapor of A. Does everybody remember that? And there's a Kahoot we can take next time to review on that. But then, so then down here we're in the liquid region. And then this region here is the VLE region, vapor liquid equilibrium, in between YA and XA. But once we get below XA, now we're below the temperature at which any of those mixtures would boil. Okay. If we keep cooling it down, eventually it'll solidify. Okay, but we're not quite there yet. The next lecture is on the solid phase diagrams. Okay. So we're in the liquid region, and let's talk about partial miscibility. Right now, we have a single phase no matter what combination we have of A and B. But we know that some things will break into two layers. So if we have a more organic phase, like a chloroform and a water, we'll have a water phase and a chloroform phase. Or hexane and nitrobenzene, we have partial miscibility in some situations. And so there may be a region down here where we have phase separation. So we're back to an equilibrium situation. So two-layer liquid. And the reason it's really two layers is because we typically have different densities for these substances. And so we'll have a layer on top and a layer on bottom. We can't say which at this point without knowing what A and B are. But we could look at A and B and say, okay, A is more, that's like chloroform. Chloroform has all those chlorines. So chlorine is very dense, very heavy atom. We put 3 of those on a methane, and it's a very dense molecule. And you can test this in the lab by just picking up a 4-liter bottle of chloroform versus a 4-liter bottle of or hydrocarbon like hexane or something. It's dramatically different. And so hexane would be on the lower end, it would be below the water layer. You could also have like a hexane layer on there too, and it would be above the water layer. So it's lighter than water, less dense than water. And so you can make a 3-layer system pretty easily. You put hexane on top, water in the middle, and chloroform on bottom. But we're not going to get into 3-component mixtures. We're just going to do 2, where we have 2 layers. Okay. And so this is the region that we're dealing with right now in the course, is this region right here. Up here it's miscible in this region. And then here we have phase separation. And so that's why we call these partially miscible systems, because at higher temperatures, they're miscible, at lower temperatures, they phase separate. One of the uses of this is a lot of times we'll use this for steam distillation, and it's how we distill heat-sensitive organics, water-insoluble organics. But let's look at the Gibbs energy of mixing. So this is what's driving this miscibility change. So we have the Gibbs energy of mixing, which is that delta S of mixing. So on our little plot here, we have the if the delta H is 0 if it's ideal, but in these situations we have non-ideal behavior. If it was ideal, we would have a miscible mixture. But because we have some enthalpy change that's a function of the composition, and if we have a difference in molar volume, a difference in densities, then we'll have a likelihood of phase separation. Okay, and so this is just solving for this upper critical solution temperature. And so here's this upper critical solution temperature, and it's wherever these so delta G is equal to delta H minus, oh, it's up here, minus T delta S. And so delta H is plotted in red, and the minus T delta S is plotted in blue. And you can see that delta G is the green curve, and there's some places where delta G of mixing is less than 0, meaning it's negative. And there's some places where delta G is greater than 0 or positive, where we don't have spontaneous mixing. So this green curve is the delta G curve for phase separation. There's places where it's negative, and so you can mix 20% of nitrobenzene in hexane. You can mix 90% nitrobenzene in hexane, but you can't mix 60% nitrobenzene in hexane. It'll phase separate. So that's really strange. And so what I've shown here is, this region here between around 0.4 to 0.8, you have 2 layers. But if you get above 0.8, you have one single layer, because it's mostly nitrobenzene with a little bit of hexane floating around in it. But if we get too much hexane, then it will form its own layer. And down here we have mostly hexane with a little bit of nitrobenzene floating around in it. But if we get above 40%, then nitrobenzene is going to segregate and form its own layer. It's temperature dependent too, because of this T delta S piece. So that the entropy piece is what makes it temperature dependent. And so if I increase the temperature, I'm pushing this blue curve further negative. And it can drag all of that green curve down to where it's all negative all the way across. And so then it's miscible. So there'd be some temperature at which this point right here touches 0 and everything else is negative. So that's this point here. That's the upper critical solution temperature. Above that temperature, you have miscible solutions. Below that temperature, you have the possibility of forming 2 layers. Now, you may have regions to the left and to the right where it's miscible, or homogeneous, I should say, not miscible, but homogeneous. And then between that curve, you have 2 layers. And again, you would use the lever rule here to figure out, let's say we had a 50-50 mixture. So our fulcrum is right here at 50-50. We've got most of our system is this layer. This is the big kid on the seesaw, right? And a little bit of our system is over on this side to balance that thing out. So let's do the calculation for this lever rule problem. So this is the upper critical solution temperature, also called the upper consolate temperature, because they were trying to shy away from the use of the word critical again, because this is not related to the critical point at all. This is just saying above this temperature you have a miscible situation, below this temperature you have a possible phase separation. But in order to get away from the use of the word critical, they call it the upper consolate temperature in some books. Okay. So let's look at this. We have Zn of 0.41. So this is Zn, and this is the fulcrum. And so let's speciate this beaker that's got 2 layers in it. Now, if we're above 292, so here's 292. If we're above 292, we have 1 phase. So you see there's no layers. And we have 41% nitrobenzene and 59% hexane. All of our moles are in that solution. But what if we get below that? If we go down to 290, we get down to 290, then this far left side is 0.35, the far right side is 0.83. So those are the compositions of our layers. Now this is a good point to make. When I was growing up as a chemist, I thought that the layers were pure, right? If you have chloroform and water, I figured the water phase was pure water and the chloroform phase was pure chloroform. It is not. Okay, there's water in that chloroform and there's chloroform in that water. Maybe not a lot, but there's some. Now in this case, we've got a lot of, this is nitrobenzene, we've got a lot of nitrobenzene in the hexane rich layer. So this side is hexane rich because this is nitrobenzene, and so it's less than 50% nitrobenzene, so we would call that hexane rich. So this is the hexane layer on this side, and this is the nitrobenzene layer on this side. So this is nitrobenzene rich on this side, so 83% nitrobenzene on a mole basis, and this is 35% nitrobenzene on a mole basis. So when we talk about the hexane layer, it has 35% nitrobenzene in it. So that's, but it's still, it's, you know, it's mostly hexane, 65% hexane. So this is what it would look like. The nitrobenzene is going to be more dense, so it's going to be on the lower, it's the lower layer. Okay. And so we have these compositions. So it's this top one, the larger layer. How do I know this is the larger layer? Well, look at where the fulcrum is. And so this is telling us that A prime is larger. And so you see over here, A prime is the larger layer. There's more moles in that layer than there are in A double prime. So A double prime is far away from that fulcrum. And so that's why I draw the little seesaw. There's a little kid on this end, and there's a big chunky kid on this end. To get that thing to balance out. Now this tells us the compositions of those layers, but it doesn't tell us the amounts. And so let's go ahead and do the lever rule and figure out how many moles of every species are in each layer. We know the mole ratio, but that's not the total number of moles. If I know I had like 10 moles of all my substances in here, now I can figure out what ratio of everything is in each layer. So Z.41 refers to the total mole fraction of N across every phase that's present. Okay, this is in the entire mixture. So in the whole beaker, it's 41% nitrobenzene. So A prime represents the hexane rich layer. That's the less dense layer, so it's on top. A double prime represents the nitrobenzene rich layer. And these values L A prime and L A double prime are called tie lines. They tie the fulcrum out to the phase diagram edges. And so this will be this will be seen in the lever rule where there's two equations and two unknowns. So we have the relative amounts of moles in each layer. So this is the number of moles in A prime. This is the number of moles in A double prime. And those numbers of moles add up to the total. So to even do a lever rule problem, we have to know this. If we don't know the total number of moles in our beaker, then we can't speciate. We can't figure out, you know, what the distribution is. We can keep the percentages. We know it's 83% nitrobenzene in the nitrobenzene layer and 35% nitrobenzene in the hexane layer. But if we know the number of total moles in the system, then we can speciate and figure out what specific numbers are in each one. So if we assume that we have 1 mole total, so our moles total of hexane and moles total of nitrobenzene add up to 1, we can use the lever rule. And so let's put in our numbers. Let's rearrange this let's bring the A prime over to this side, and let's bring the L over to that side. So we've got Na prime over Na double prime, and that's equal to La double prime over La prime. So this is the key here. Look at these numbers. This is 83 minus the 0.41. So that's this distance right here. 0.83 minus the 0.41. You see that that's the length of that line in that phase diagram? See how it's related to the phase diagram? And then in the denominator, we have the 0.41 minus the 0.35. That's the length of this small piece over here. And that goes in the denominator because that's this piece right here. We do this subtraction on the numerator and the denominator and then divide, and we get 7. So there's 7 times more moles in the upper layer than in the lower layer because of the temperature that we're at and where our fulcrum is. And so then we could say that Na is 7 times Na double prime. And we know that if we add those two pieces together, they equal 1. So we have the total moles in each layer add up to 1 mole total. And that was given in the problem. So we're assuming that we have 1 mole total here. So they should add up to 1 mole. So I end up with Na double prime being 1/8 or 0.125 moles total in A double prime. And then I know that Na prime is 7 times that. Okay. Or 8.875 Na prime. So this is the number of moles in this top layer. And this is the number of moles in this bottom layer, a tiny little bit. Okay. So that's good. We now know how many moles are in each layer. Now we can use the mole fractions in each of those to come up with the moles of nitrobenzene and moles of hexane in each of the layers. So this is in A prime. A prime has this many total moles, and it is 0.35 mole ratio of nitrobenzene in moles total. So the moles total cancel, and we end up with 0.31 moles of nitrobenzene in A prime. So that's how many nitrobenzene moles are in this layer right there. And 0.65, 1 minus that, 0.65 moles of hexane in the total moles. And so we end up with 0.57 moles of hexane in that layer. Because that's the composition of that layer. We determined that it has 7/8 of the moles, and so of that 7/8 of the system, 35% of that is nitrobenzene, 65% of that is hexane. Now let's do the A double prime layer. It's 0.83 moles of nitrobenzene, but we only have 1/8 of our total moles is in that second layer. And so it's 0.1 moles of nitrobenzene in this tiny little layer down here. And then 1 minus the 0.83 is 0.17. And that's the amount of hexane that's in that layer. So the moles total cancel, and we end up with 0.02 moles of hexane in this layer. Now the nice thing for lever rule problems is you can check your work at the end. You can add them all up, and they should all add up to 1. Okay. And so you can check it in 2 ways, 0.31 plus 0.57 plus 0.1 plus 0.02. That gives us 1 mole total, so that's good. All of our species add up to 1 mole, the total. And then we could do the overall composition. So I have 0.31 moles of nitrobenzene in the big layer and 0.1 moles of nitrobenzene in the smaller layer, and that adds up to the 0.41 moles of nitrobenzene in the whole system. That's the Z value. So we can check our numbers that way. So that's the lever rule problem. It's really 2 steps. You have to have the total number of moles, and you break that into the 2 layers.
And if they were doing a gas phase equilibrium or something, you would break that into the gas and the liquid phase, and then you would look at their molar values for their volume or whatever, and you could speciate that. So we could, I'll ask you some review questions here at the end. So this is some graphs that I got out of that Excel spreadsheet that I made, making the upper critical solution temperature. And so if we're at room temperature and we've got a beaker of hexane and we start adding nitrobenzene to it, okay, at what composition does phase separation start to occur? Right here. So this is 0.3, 0.35, so about 0.36 or 0.37. You see that? As we're adding nitrobenzene, once we get above 0.36, then we're going to start to form a tiny little layer of nitrobenzene in the bottom. If we keep going to here, at 0.6, we have about, well, maybe it's slightly less than that, 0.57 or so. These two lines are about the same. And so there we have the same number of moles in each layer. That's saying that the same number of moles, yeah, in each layer. Okay. We get over here. Now we've added so much nitrobenzene that the hexane layer is really small. And if we add any more nitrobenzene, the hexane layer disappears and it's a homogeneous solution. Doesn't mean it's pure nitrobenzene. I mean, it's still, like right here, still has 85%, it's 85% nitrobenzene, so it's still 15% hexane, but we don't have a hexane layer. So only between that semicircle or ellipse do we have two layers. Anything outside or above, we have a homogeneous solution. Inside, we have a heterogeneous solution. We have two layers. So pretty cool stuff. This is partial miscibility. Okay. We'll look at some crazy ones next time, and then we'll get into solids.